Welcome back to Vision Vitals, the one corner in the podcast universe you can trust to deliver insights on embedded vision. We at Econ Systems are once again thrilled that you're all ears. Today, we'll be discussing a comparison that comes up constantly in robotics, navigation, industrial automation, and smart machines. Time of flight versus stereo. Both generate depth. Both help systems understand spacing and structure, and both deliver distance information frame by frame. But where they work and where they don't can be different. In this episode, we're going to compare how they behave, where they diverge, and why some applications lean heavily toward one approach over the other. Good to have you here.
Happy to be here. Stereo and ToF solve the same problem, but their underlying principles make them react very differently in real deployment. Once you understand those mechanics, the choice becomes far clearer.
When product teams start evaluating depth sensing, what early cues usually signal whether a scene leans toward stereo or is better served by a time-of-flight setup?
One of the earliest cues is scene detail. Stereo needs texture, edges, and variation across the frame for the algorithm to match features between the two sensors. If the scene includes smooth surfaces, uniform boxes, matte walls, or low-detail objects, stereo loses the references it needs for disparity. ToF, by contrast, is independent of texture because it measures distance based on reflected NIR light. Therefore, environments filled with smooth packaging, dark materials, or surfaces with minimal visual pattern immediately push the decision toward ToF. Another early indicator is lighting stability. Stereo performs well outdoors and in scenes with strong ambient illumination. ToF brings its own illumination, enabling reliable operation in low-light or nighttime conditions. Indoor automation, dim warehouses, and shaded factory zones usually push developers toward ToF. Very early in their evaluation,
How does the way stereo reconstructs depth differ from how ToF measures it, and how does that difference impact the final depth map?
stereo uses two synchronized sensors placed at a fixed baseline. The system compares both images, searches for feature matches, and measures how far those features shift horizontally. That horizontal shift, called disparity, translates into depth through triangulation. The catch is that stereo must run a computationally heavy correlation process, and the output depends strongly on scene texture and lighting uniformity. ToF takes a completely different route. It emits near-infrared light, captures the reflected signal, and derives distance from the travel time or phase shift of that returning light. That means every pixel gets a direct measurement. The result is a dense depth map that remains stable across flat surfaces, dark materials, and low-detail scenes, as long as the illumination strength suits the working range.
One topic that always comes up is accuracy. Based on the numbers in the comparison tables, how do their accuracy characteristics differ across real deployment ranges?
Stereo operates in the centimeter accuracy bracket because its accuracy depends on resolution, baseline, and the ability to find clean disparity levels. Increase resolution and baseline, and the accuracy improves, but at the cost of size and processing. ToF lands in the millimeter to centimeter zone, depending on range and illumination strength. Because the distance calculation is based on timing rather than feature correlation, accuracy stays consistent even when surfaces lack texture. For shorter to mid-range tasks like spacing checks, navigation corridors, and obstacle detection, ToF tends to deliver more predictable accuracy across changing scenes and lighting.
Lighting is one of the biggest deciding factors in depth performance. How do stereo and time of flight behave when lighting shifts between bright zones, dim corners, and low reflectance surfaces?
Stereo depends entirely on the available illumination because both sensors capture natural light from the scene. When lighting is normal and reasonably bright, stereo produces strong disparity levels and clean depth. But when the scene moves into dim corners, shaded racks, or areas where the exposure drops, disparity weakens and the match confidence falls. ToF brings its own near-infrared output, so it stays steady across lighting changes. Even when surfaces are dark or lightly reflective, the depth remains consistent as long as the emitted signal returns with enough strength. This gives ToF an advantage in warehouses, indoor robots, and low-light navigation, where lighting isn't guaranteed. Outdoors, stereo gains the upper hand again since strong ambient illumination helps detail.
The comparison tables highlight software load as a core differentiator. How should teams think about the processing requirements of stereo versus ToF?
Stereo relies on a feature-matching pipeline. The system searches for correspondence points between the left and right images, computes disparity, filters errors, and converts those disparities into depth. This full correlation path consumes processing cycles, especially at higher resolutions where the search space grows. ToF distributes the work differently. The distance value is baked into the signal returning from the sensor. Instead of matching features, the depth processor simply interprets the phase or timing shift across pixels. That means fewer algorithmic stages, lighter post-processing, and more predictable load on the host. The practical outcome is this. Systems with strict compute budgets, or those running multiple pipelines in parallel, usually find ToF easier to integrate at scale. Stereo, on the other hand, rewards platforms that already invest in GPU or accelerator resources.
Depth range is another major factor. How do these two technologies scale when applications need short-range precision or longer mid-range coverage?
Stereo's usable range is shaped by its baseline and resolution. Increase the baseline, and you extend the range, but the module becomes physically wider. Increase resolution, and you push accuracy further out, but at a higher computational cost. As a result, stereo can scale, but changes require mechanical adjustments or processing overhead, and that limits how far teams can push it inside compact systems. ToF scales through illumination strength. Add more VCSL units or tune the emitted power, and the depth range extends without expanding the physical width of the camera. That's why ToF modules maintain a compact footprint even when designed for mid-range sensing. If a project needs tight near-range accuracy for pick-and-place or extended coverage for navigation corridors, ToF tends to scale with fewer trade-offs.
Surfaces inside factories, warehouses, and outdoor areas vary wildly. How do stereo and ToF respond when materials swing between reflective metals, dark materials, matte cartons, and transparent sections?
Stereo succeeds when it can find visible patterns. Reflective or glossy surfaces distort those patterns, making it harder to stabilize disparity. Dark materials reduce contrast, which also lowers stereo's confidence. Matte cartons with good texture behave well, but transparent or semi-transparent materials cause depth discontinuities because edges don't appear consistently across both sensors. ToF reacts based on signal return strength, not pattern recognition. Reflective materials can scatter NIR light unpredictably, but the system still captures usable returns after filtering. Dark materials absorb part of the light, yet ToF continues producing depth as long as the emitted power suits the working range. Transparent areas remain challenging for both, but ToF handles mixed material scenes more predictably because the depth calculation doesn't depend on surface details.
Outdoor scenes introduce their own complications. How do both technologies cope when sunlight, shadows, and strong ambient peaks keep shifting through the day?
Stereo naturally benefits from strong ambient light. Bright daytime scenes give both sensors high contrast and rich detail, so disparity stays reliable. Even when shadows move through the frame, stereo can still track depth as long as edges and textures remain visible. ToF's behavior depends on the wavelength chosen. Outdoor scenes introduce high-intensity ambient peaks that compete with the emitted NIR signal. This reduces the contrast between the outgoing light and the returning reflection. That's why outdoor-focused ToF modules often use 940 nm illumination to stay farther from ambient peaks. With proper filtering and calibrated illumination strength, ToF maintains depth outdoors, but its consistency varies compared to stereo's naturally robust daytime performance. For platforms that operate through the full light cycle, both approaches require tuning, yet stereo typically starts with an inherent advantage in bright conditions.
Cost often influences early decisions. Based on the comparison tables, how should product teams interpret the cost structure differences between stereo and ToF?
Stereo uses two standard 2D sensors, a fixed baseline, and optics. This keeps the material cost low, especially when teams stay within common resolutions. The cost lies mostly in compute, tuning, and the effort required to stabilize depth across varying scenes. ToF carries more specialized hardware, a NIR-sensitive sensor, illumination module, laser driver, cover glass, and depth processor. That places it in the medium material cost bracket. However, because the depth arrives pre-processed, downstream compute and algorithmic integration tend to be lighter and more predictable. Therefore, the trade-off is simple. Stereo offers hardware affordability, but shifts complexity to software and tuning. ToF asks more of the hardware bill of materials, but simplifies everything that follows. Teams should weigh where they prefer to spend their optimization time, on hardware stability or on software effort.
That wraps up our audio exploration into how stereo and time of flight approach the same problem through two very different paths. If you're mapping out a new robot, automating a process, or upgrading a sensing pipeline, these contrasts give you a far clearer idea of where stereo shines and where ToF brings more consistency. For teams exploring depth solutions, you can find more details at econsystems.com. Thanks for spending your time with Vision Vitals today. We look forward to having you back for the next episode.